Thank you, Dr. Benavides. Thank you, panelists. Good morning, everyone. My name is Benedict Gray. As Dr. Benavides said, I am the principal investigator for the Invictus design team, and today we will be presenting to you the Vesta System validation review. What this presentation will cover is a mission summary, our concept of operations, the Vesta subsystem validation, Vesta system validation, and then our conclusions and programmatics. Presenting with me today is Jason Hamburger, Lucas Siskowski, Renee Spear, Brandon Dudley, Kyle Walker, Julia Mihailov, and Shane Evan Sanchez, a member of the integration team. Not with us is Jonathan Hamburger, as he presented in the previous presentation to cover the communications of the Vesta system. Moving forward, I would like to remind everyone of the structure of our class. There were 20 people during the preliminary design phase and 19 during the detail phase. We were divided into two teams, the Invictus design team led by myself and the Endeavor design team led by my colleague Barrick Smith. We had Manfred Hamburger leading us as our project manager, and we had Gino Farah as our assistant project manager, who has been kind enough to man the station for us. Road 1 is reconnaissance operation for guided unmanned exploration 1, and its purpose is to obtain visual data of a remote location with unmanned vehicles. What you can see pictured on the screen is concept art for two of the three constituent systems of the Road 1 mission, the Vesta UAV and the ERAU rover. The third constituent system is the ground station, which was covered in the previous presentation. It consists of a patch antenna, modem, power over Ethernet adapter, network switch, and 3 laptop computers. It is what is used to communicate with the vehicular systems during the mission. What you can see pictured now are the 2 vehicular systems as of completing their conformity inspection earlier this semester. I would now like to go into the concept of operations of the mission with an animation. It begins with phase 1, pre-flight, where the ground station is set up in the executive conference room on the 3rd floor of this building. These systems are then taken to the Mos Eisley Spaceport, the rotunda at the Embry-Riddle Lower Fields. That's where they are set up, and a preliminary check is done to ensure that all systems are functioning nominally. Our target area is the Yavin 4 ruins, the barbecue complex at the right of this image. The Vesta system is constrained to fly only within the hyperlane, which is bounded by the northern soccer field and the southern field. Phase 2 begins transport to the Yavin 4 ruins, where the Vesta system takes off, travels through the hyperlane passing multiple obstructions, 3 light posts, and an electrical box enclosure. It then lands about 20 meters from the barbecue complex, the Yavin 4 ruins. Once it is landed safely, phase 3 begins deployment of ERAU, where the servo docking mechanism is released, allowing the ERAU rover to exit the payload interface. Once the rover has exited the payload interface, we enter phase 4, reconnaissance of the Yavin 4 ruins, where the ERAU system navigates through the Yavin 4 ruins and takes pictures at various locations and times to survey the area. These are then supplied to the customer after the mission. Once it has successfully surveyed the area, it will return to the Vesta system during phase 5, docking with Vesta, where it drives back into the payload interface, and those servo docking mechanisms are lowered in order to constrain the system during the return flight. At this point, we begin phase 6, return to Mos Eisley Spaceport, which is a secondary objective, thus not required for mission success. To note, the 2 flights were sped up for the sake of time. We expect them to, in reality, have lasted about a minute. Once we have landed, we enter phase 7, post-flight. This is when all of the systems are checked to make sure they are safe to approach, the mission environment is cleaned up, and everything is taken back to its storage location and data analyzed. What you can see on the screen here is the design that the 2 design teams generated to meet the objectives and constraints of the Road 1 mission. Again, it consists of 3 systems, Vesta, ERAU, and the ground station. This presentation will cover the Vesta system, which consists of 5 subsystems: structures, communications, electronic power, onboard computer, and propulsion and attitude control. Again, we will omit the communication subsystem as it was covered previously, and we will only go into the component validation as required. I would now like to welcome up my colleague Jason Hamburger to go over the structure subsystem validation.
Thank you, Ben. So I'm Jason Hamburger. I'm going to be covering the structure subsystem. On the screen is the structure subsystem with respect to the other partitions of the design structure tree. Of note is the aerial structure, the landing system, and the payload interface components that comprise the structure subsystem. The objectives for the structure subsystem is that it should sustain the structural forces incurred during the mission. It should provide a frame for mounting the other subsystem components, and it should secure the ERAU system to the structural frame during the to the Vesta system during the mission flight, and it should deploy the ERAU system upon landing. The critical components that satisfy these objectives is that the aerial structure component shall sustain a thrust force of less than or equal to 300 newtons generated by the propeller's component. The landing system component shall be capable of withstanding less than or equal to 12,740 newtons, and the payload interface component shall sustain less than or equal to 120 newtons applied in the nadir direction. Pictured on the screen is our design solution to meet these requirements and objectives. Of note is the aerial structure component, which is on top and consists of 6 T-beams and 2 torsional struts. And then joining the arms, the T-beam arms, is the landing system components, which consists of 4 legs, and then the payload interface component is then attached to those legs. Additionally, the payload interface component consists of 2 servo motors, which are used during the mission to secure the ERAU system to the structure. In terms of numerically analyzing and validating our requirements, we generated ANSYS models for the aerial structure component. On the screen here is our solution for the mounting plate for the aerial structure that joins together all of the T-beams. And here we were able to successfully withstand 300 newtons. On the slide here is our T-beam analysis, again in ANSYS, where we applied a 300 newton result, and this is the nodal solution pictured, in which case we were able to withstand the 300 newton force generated by the propeller's component. In terms of experimentally validating these, we turned the structure upside down and applied weighted rice bags. Each bag correlates to 1 kilogram of weight, and so since it's upside down, it's generating that lift component. Unfortunately, when we went to first test this, we only had 1 mounting plate, and we weren't able to pass. We only got up to 2 bags of rice, and we needed 5 on each arm to get that 300 newton result. And so we had to do a quick redesign, in which case we added a bottom mounting plate to help sandwich the T-beams together. And at this time, we were able to visually meet these 300 newtons and not have any deformation or plastic deformation that was critical to the structure. However, due to lack of experimental data collected, we weren't able to properly numerically validate this experimental result. At this time, I'm going to welcome up Lucas Zazowski, who's going to continue covering our landing system component and our payload interface component requirement validations.
All right, thank you, Jason. The landing system, there we go. Landing system component was numerically validated by creating an ANSYS model and applying appropriate pressures and constraints. We then took the maximum stress found in that model and compared it to the ultimate tensile strength of carbon fiber. The maximum stress was less than this, which therefore validates the component. We experimentally validated the landing system component by making a test specimen landing leg and placing it in the tensile tester in AXFAB. We then applied increasing amounts of force until it fractured. In the stress strain diagram, you can see that the test specimen withstood 18,112 newtons before it fractured. This is above the 12,740 required. Therefore, the landing system component was experimentally validated. Just in summary, the landing system component was numerically and experimentally validated. The payload interface component was numerically validated by, once again, creating two ANSYS models this time for the two parts of the payload interface. The correct pressures and constraints were added to it. The maximum, so this is the right-hand part of the payload interface, and this is the left-hand part. The maximum stresses were taken and compared to the ultimate tensile strength of the ABS plastic used this time, and was found to be less than the ultimate tensile strength. Therefore, the payload interface was numerically validated. We attempted to experimentally validate the payload interface by taking a board, putting in the payload interface, and adding 1 kilogram rice bags onto it until we reached 120 newtons. However, since no data was taken, we could not successfully experimentally validate it at this time, only visually. Also, to note, during 2 chaotic landings of Vesta, we had 2 payload interfaces fracture. They're up there on the table if you'd like to take a look at them later. After the second failure, we redesigned the payload interface to be made out of 5052 aluminum, which seemed to do the trick. The payload interface did not fracture after Vesta's final flight. It's on that video. In summary, the aerial structure, the landing system, and the payload interface were all numerically validated, while only the landing system component was experimentally validated. The aerial structure and the payload interface were not experimentally validated at this time. I would now like to welcome up Renee Spear, who will be talking about the propulsion and attitude control system.
All right, thank you, Lucas. I will now begin the discussion of the propulsion and attitude control subsystem. To begin with, this subsystem lies beneath the Vesta system in our design structure tree and has 3 items at the component level, which are attitude sensors, motors, and propellers. There are 4 primary objectives for the subsystem, which include that it should transport the combined Vesta system and ERAU system between the Mos Eisley spaceport and the Yavin 4 ruins. It should provide stable flight for the combined Vesta system and ERAU system during flight. It should transmit attitude data to the onboard computer subsystem, and it should transport the combined Vesta system and ERAU system autonomously. In terms of constraints, this subsystem will operate at wind speeds less than or equal to 3.2 meters per second at 10 meters of altitude, and it will operate in optimal weather conditions. There are 8 requirements for this subsystem, with the first 2 being that it shall be capable of providing a thrust-to-weight ratio greater than or equal to 1.5 to 1, but less than or equal to 4 to 1 with reference to the carrying load. It shall have a pitch angle less than or equal to 64.8 degrees, but greater than or equal to negative 64.8 degrees. It shall also have a roll angle less than or equal to 64.8 degrees, but greater than or equal to negative 64.8 degrees. And it shall have a pointing accuracy greater than or equal to negative 5 degrees, but less than or equal to 5 degrees. The design shown on the slide shows the solution that we've engineered in order to satisfy these objectives, constraints, and requirements. This includes 6 18-inch by 5.5-inch ABS with carbon fiber inlay propellers, 6 high-max electric motors, 7 ultrasonic rangefinders, 1 IMU unit, 1 GPS unit, and 1 Pixhawk flight controller. As noted in the previous presentation, the Pixhawk was not part of our original design. We ended up changing during our design iterations, but the reason for this change will be discussed in later in the presentation. Additionally, our previous designs used the E-Flight Power 60 brushless outrunner motors, but due to weight constraints, we ended up changing to the Himax HC 5018-530 motors. However, before we made the design change, we completed experimental tests with the E-Flight motors, for which we used that data in order to numerically validate our first 2 requirements within the subsystem through a derivation of the capabilities and characteristics of the Himax motors and the E-Flight motors. And through this derivation, we determined that our Himax motors are capable of providing a 1.5 to 1 thrust-to-weight ratio at 54% throttle and a 3.4 to 1 thrust-to-weight ratio at 100% throttle. Both of these values fall within the range set by our requirements. We are also able to numerically validate these requirements using a software called JavaProp, for which we took a geometry input file of our propeller, which the design you can see was on the screen was drawn by the software itself. And then we requested a data output of thrust, and from this data we determined that we are capable of producing a 2.16 to 1 thrust-to-weight ratio, thus also numerically validating these requirements. Additionally, we experimentally validated these requirements using a thrust test stand for which we used to perform thrust tests on each motor and propeller combination. In order to do so, we used a load cell and LabVIEW to collect the data, and we constructed the test such that in the first half second of the test, we raised the percent throttle from 0% to 100% in increments of 25%, and every 3 seconds after that, we dropped it down by 10%. Now we have a short example of a test for you. Well, there was sound with the video, but basically you can just hear the propeller running, and then you can hear it drop as the percent throttle drops, hear the RPMs drop. Once we completed each test for each motor and propeller combination, we analyzed the data. Of note, the data on the screen is at 65% throttle and 100% throttle. The reason we analyzed these percent throttles was because our mission was designed to be conducted at approximately 65% throttle as average, and then we looked at the 100% in order to validate our maximum thrust to weight ratio requirement. Based on the combined thrust produced by these motors, as well as the combined weight of the system of systems, we determined that we were capable of producing thrust to weight ratios of 1.93 to 1 at 65% throttle and 2.85 to 1 at 100% throttle. Overall, in summary, we were capable of numerically and experimentally validating both of these first two requirements dealing with our thrust to weight ratios. Now I'd like to welcome up Brandon Dudley to continue the discussion of the propulsion and attitude control subsystem.
Thank you, Renee. To further expand upon the PixHawk 2.1 flight controller, this was added about halfway through the semester by Team Invictus to the propulsion and attitude control subsystem in order to help mitigate some of the problems that were arising as we were trying to build our own control law and control code itself. This also helped us with the experimental validation of the remaining 6 requirements of the propulsion and attitude control subsystem. The 4 requirements seen on screen are those that pertain to the pitch and roll requirements for propulsion and attitude control subsystem, and these were numerically validated through 2 equations that set boundaries on both of these edges so that we could maintain static thrust for the Vesta system as we flew from the Mos Eisley Spaceport to the Avenfor ruins and back. We wanted to maintain this static thrust so that we did not decrease in altitude as we were flying before we were ready to actually begin the landing procedures. The experimental validation was done through analysis of the PixHawk flight logs from 2 different flights. We have one which was a stable flight test, one of the VTOLs, and we had another test that was the actual crash of the Vesta system, which is the unstable flight test. As can be seen, the stable flight test falls within all 4 requirements, meeting those requirements, not exceeding that 64.8 degrees in positive or negative. However, the experimental flight test, the unstable flight test does not experimentally validate the final requirement for roll exceeding that 64.8 degree requirement, hitting a 77 degrees. We partially relate the eventual failure of the Vesta system and the crash to us exceeding this roll requirement and not being able to maintain a constant altitude as we are flying. The numerical validation of the pointing accuracy requirements was done through the selection of the hardware for the IMU itself. We wanted to maintain this pointing accuracy so that we did not have to overcorrect the system as we were flying, so that the batteries could have the maximum amount of time for the flight there and back itself. The experimental validation of these requirements was conducted through similar manner to the previous 4, going over flight log data and looking at the yaw value this time. As can be seen with the stable flight tests, we were able to experimentally validate these requirements. However, there are 2 instances of us not experimentally validating these requirements in the unstable flight test. When we actually looked at the graphs of our yaw values, Team Invictus did come across something that we had not intended with the requirements. We only exceeded these requirements in, for about 1 second in the overshoot of the system that quickly balanced itself out, which did not meet the true spirit and intention of how we intended this requirement to be. We wanted to minimize how much we would have to correct the system, but this overshoot did not present a large deviation for the flight itself. As such, if we were to move forward, Team Invictus would look at reworking or rewording these requirements in order to better fit the spirit and true intention of what we wanted out of these requirements. So in summary, all 8 of the propulsion and attitude control requirements were numerically validated. However, only 5 of them were experimentally validated. I would now like to welcome up Kyle Walker, who will be going over the onboard computer subsystem.
Thank you, Brandon. Pictured on screen is the onboard computer subsystem in relation to the other partitions of the design structure tree of the Vesta system. There are 5 objectives for the onboard computer subsystem: that it should perform all computations required by the carrier vehicle, that it should interface with both the communication subsystem and all sensors on board of the carrier vehicle, and that it should save all input and output data. Furthermore, there are 5 constraints placed on the onboard computer subsystem: that it will assist the electrical power subsystem in regulating the electrical power supplied to hardware interface with the onboard computer subsystem, that it will provide both a power over Ethernet port and a powered USB port, and that it will provide both I2C and SPI interface protocol capabilities. From these, 27 requirements were generated. However, for the sake of time, we will only be covering the critical requirements of this subsystem, and we will be jumping into the design of it, which includes a Raspberry Pi 3 Model B+, along with an Adafruit 16-channel PWM servo hat, along with 2 Adafruit 4-channel ADCs, and a 16GB microSD card. Pictured on screen is the full Vesta system wire schematic, which describes how the full system is wired together. We would be happy to expand upon this upon request. For clarification, the Raspberry Pi 3 Model B+ is pictured on the left of the screen, and with its 16-channel PWM servo hat is pictured on the right. The specifications for the Raspberry Pi 3 specify that it has a processing speed of 1.4 gigahertz, which numerically validates our requirement to have a processing speed of greater than or equal to 8 megahertz. When tested, we found that the processing speed was the specified 1.4 gigahertz, thereby experimentally validating this requirement. The original selected microSD card had a storage capacity of 16 gigabytes, which was greater than or equal to the required 0.5 gigabytes of storage capacity. However, as we began to develop the software for the Vesta system, we soon found out that in order to have enough storage capabilities for all of the Python libraries required to support our software, we needed to use a 64 gigabyte microSD card, and then with the later addition of the PixHawk 2.1 flight controller, we utilized an 8 gigabyte microSD card to store flight logs. This brought our total storage capacity to 72 gigabytes, which also experimentally validates this requirement. The Adafruit 16-channel PWM servo hat provides 16 GPIO pins, along with pins that provide I2C and SPI protocol capabilities, along with 16 PWM signal pins. These, then our selection of 2 ADCs use I2C protocol, along with, and each contain 4 analog pins, bringing our total provided number of analog pins to 8. All of this numerically validates the requirements set on the number of pins required. When we went through and tested the configurations of these pins, all of them were configured properly. This experimentally validates these requirements. Furthermore, the Adafruit 16-channel PWM servo hat provides a 5V rail, a 3V3 rail, and a ground rail, each with 5 pins. The 3V3 rail is internally regulated from the power source to approximately 3.3 volts, and the 5-volt rail was externally regulated using a DC to DC step-down converter, which could be calibrated to output the required voltage between 4.7 and 5.5 volts to the servo hat. All of this numerically validates the requirements set on the output voltages from these pins. When we went through and tested the voltages, we found that the output voltage from the 3V3 line was 3.3 volts, and that the output from the 5V line was 5.3 volts, which falls within the required tolerances of the 5-volt rail. All of this experimentally validates the output voltages. There was a separate 5-volt line supplied to the power line for the PWM servo ports, which powered our servo motors. This separate 5-volt line was also externally regulated through the use of a separate DC to DC step-down converter, which could also be calibrated to the required greater than or equal to 4.8 volts and less than or equal to 6 volts. Numerically validating these requirements. When we calibrated it, we found that we calibrated it to output a voltage of 5 volts, experimentally validating these requirements. In summary, all of the critical requirements of the onboard computer subsystem have been both numerically and experimentally validated. At this point, I would now like to welcome Julian Mihailov, who will be covering the electrical power subsystem.
Thank you, Kyle. Shown on the screen is where the electrical power subsystem lies with regard to the other partitions of the design structure tree. To note, there are two components, including the power supply component as well as the power regulation component. The electrical power subsystem objectives include that it should house the power supply component as well as the power regulation component. The critical component requirements of the electrical power subsystem include that the power supply component shall be capable of supplying greater than or equal to 860 watts of mean average power to each motor within the motor's component of the propulsion and attitude control subsystem over the total duration of its life, and be capable of supplying greater than or equal to 100 watts of mean average power to the onboard computer subsystem over the mission duration. And the power regulation component shall regulate the amperage supplied to the onboard computer subsystem to less than or equal to 2.6 amps, as well as regulating the voltage supplied to the onboard computer system to greater than or equal to 4.75 volts and less than or equal to 5.25 volts. Shown on the screen is the design we have created in order to satisfy these objectives. To note are the 6 motor batteries, the 6 electronic speed controllers, the 7 voltage sensors, the component battery, as well as the DC-DC step-down converter. Shown on the slide here is a block diagram of the motor wiring. Starting with here, we have the motor, which is then connected to the electronic speed controller, which is then connected to the motor battery, to a voltage sensor, which monitors the present depth of discharge of the motor battery, which is then connected to an ADC, and breadboard and motherboard. The motor battery was designated to be Venom Fly 30C 2500 milliamp hour 6S LiPo batteries, which are interfaced with 6 Skywalker 60 amp UBEC electronic speed controllers. The motor battery is capable of outputting 860 watts at a maximum duration of 3.1 minutes, which numerically validates this requirement. We also ran this battery at 900 watts, also experimentally validating this requirement. On the shown on the slide here is the block diagram of how the component battery powers the rest of the electrical components, which we can go into further detail upon request. Thank you. The component battery is capable of outputting 100 watts at a maximum duration of 38.4 minutes. Very good. Thank you. Numerically validating this requirement, and we also ran this battery at 100 watts at the approximate duration of 38 minutes, experimentally validating this requirement as well. In order to regulate the amperage supplied to the onboard computer subsystem, we use an inline fuse holder along with a 2 amp 32 DC volt fuse, numerically validating this requirement, and we also conducted a destructive test with the fuse failing at 2.2 amps, still experimentally validating this requirement. In order to regulate the voltage supplied to the onboard computer subsystem, we use a 3 amp DC buck converter, which is capable of being tuned to a desired voltage, numerically validating this requirement. And in a test, we tuned it to the 5 volt requirement, experimentally validating this requirement, these 2 requirements as well. In summary, we have successfully, numerically, and experimentally validated the electrical power subsystem critical component requirements. And at this time, I would like to welcome Shane Evans-Sanchez to continue the discussion of the Vesta system.
Thank you, Julia. Here's the Vesta system with relation to the Rogue One design structure tree. The Vesta system has 5 objectives. The primary objectives are as follows. The system should transport the OR system from the Mos Eisley spaceport to the Yavin 4 ruins. The system should deploy the OR system after landing in an approved landing area within the Yavin 4 ruins, and the system should be operated under autonomous control. The secondary objectives are as follows. The system should relay the photographic data from the OR system to the ground station, and the Vesta system should transport the OR system to the Mos Eisley spaceport after the OR system has returned. The Vesta system has 6 constraints. The system will land in a grassy portion of the Yavin 4 ruins. The system will return to the Mos Eisley spaceport in less than or equal to 60 minutes upon leaving it. The system will have a budget for the development and operation of the Vesta system that is less than or equal to 2,000 United States dollars. The Vesta system will have a flight time of less than or equal to 5 minutes. And the system will be capable of ascending to an altitude that is greater than or equal to 3 meters, however, less than or equal to 120 meters. From these, we have generated 5 requirements for the system. The system shall be capable of a ground speed of 5 meters per second. The system shall be capable of an ascent and descent speed of greater than or equal to 0.4 meters per second. The system shall have a mass of less than or equal to 9.5 kilograms. And the system shall have planar dimensions that are contained within a 3-meter diameter circle. Here's the design solution we have engineered to satisfy these objectives, constraints, and requirements. The first 3 requirements were numerically validated using a program called JavaProp, as explained by Renee Spear earlier in the presentation. With this program, we input the physical dimensions of our propellers into the program and generated a thrust curve based on revolutions per minute. From this data, we determined that we can numerically validate these 3 requirements. The second and third requirements were experimentally validated during our final flight test. However, the first requirement was not experimentally validated as we were unable to perform a lateral flight test following our final flight test. For the experimental validation for the second and third requirements, we obtained velocity curve versus time from the PIXOC 2.1 automatic flight log. From this graph, we obtained an ascent speed of approximately 1.5 meters per second, thus experimentally validating the second requirement. And our descent speed, although unintentional, was 6.3 meters per second, thus experimentally validating the third requirement. The mass requirement was numerically validated using a combination of modeling and simulation with our CATIA model, with which we applied material properties and obtained estimated weights, along with specification sheet weights of our components and physical measurements of different components that were included on the system. Summing all of these up, we obtained an estimated total Vesta system mass of 9.46 kilograms, thus numerically validating this requirement. Pictured on the left is one of our team members holding the Vesta system on top of a wooden platform on top of an analog scale. This was the method we used for experimentally validating this requirement. On the right is the final weight measurement of the Vesta system right before our final flight test. Please note that the scale is rotated to account for the weight of the wooden platform that the system is sitting on. And as you can see, the final system weight was approximately 8.92 kilograms, thus experimentally validating this requirement. The planar dimension requirement was numerically validated using the CATIA model of our system, measuring the tip-to-tip distance of the propellers in their outboard configuration. As you can see, the final planar dimension was approximately 1.482 meters, thus numerically validating this requirement. Pictured on the right is the experimental validation for this requirement, where we used measuring tape to measure the tip-to-tip distance of the propellers, again, in their outboard configuration. And the final planar measurements that we obtained was approximately 1.48 meters, thus experimentally validating this requirement. In summary, the 5 requirements were all numerically validated. The first requirement was not experimentally validated, again, because we were unable to perform a lateral flight test following our final flight test. However, the remaining requirements were experimentally validated. Now I'd like to welcome up Benedict Ray to conclude our presentation and go over programmatics.
Thank you, Shane. At this time, we would like to share with you our most notable flight test videos. Moving forward into this first one, this is one of our earliest flight tests. We had the system anchored to the ground with rope, such that if it were to become unstable or uncontrollable, we wouldn't pose a risk to any personnel in the location. As you can see, we are able to achieve, pardon me, it doesn't seem to have started. Thank you, Gino. As you can see, we were able to achieve lift. We tell it to ascend to 1.2 meters, and when we are comfortable that it's stable, we tell it to land. Moving forward, one of the next tests we conducted was an attempted full throttle test. What we did is something similar to the aerial structure test that Jason shared with you earlier, where we weighed the system down with rice bags that were each 1 kilogram until the total system weight was 300 newtons. We experimentally validated that the motors could produce at least 300 newtons, so we expected this test to be successful. However, we were never able to directly control the throttle of the motors. It was done automatically through the Pixhawk. And as you can see, we tell it to take off, but the motors never reach 100% throttle and thus never produce enough thrust to achieve lift. Moving forward, this is our most successful vertical flight test. We tell the vehicle to ascend to 3 meters. It ascends stably and approaches the waypoint that we have told it to approach. As you can see, there is slight variation in its latitude and longitude, as well as altitude. This is a result of the controller of the Pixhawk 2.1. This is because it is a deadband combined with a PID system. Once we were confident that the system could maintain its altitude, latitude, longitude, and stable attitude comfortably, we tell it to land. It descends at a safe velocity, and it touches down on the ground softly. We then examined the vehicle and found no structural damage after this test. Finally, I'd like to move forward into our last flight test. Of note, this test was conducted at night because during April we found it difficult to find time where we could meet our wind speed constraint. This was conducted at night such that we could meet that 3.2 meter per second limit. As you can see, the system ascends. We tell it to go to an altitude of 5 meters. It then becomes unstable and falls to the ground. The Pixhawk 2.1 recorded that the system ascended to 8 meters, and we aren't entirely sure why it didn't ascend to where we told it to, but we think that there might be error in the barometer measurement. So while it said 8 meters, it was probably more realistically the 5 meters that we told it to go to. Moving forward, Gino, could you please? Thank you very much. One of the theories that we had for why this system might have failed was related to a previous test which became unstable. We determined that there was a spike in the magnetic field during that previous test. And what you can see here is the X, Y, and Z body axes during the test that was just shown. As you can see, there are spikes. However, when you look at this graph, the magnitude of the magnetic field doesn't show any such spikes. Because of this, we concluded that the spikes in the previous graph were a result of the instability and crash, not a cause. As mentioned earlier during the previous presentation, we believe that one of the main factors for this crash was the fact that the Pixhawk 2.1 doesn't allow the inertia tensor as an input to the controller. Because of this, it doesn't have a strong sense of what the dynamics of the vehicle will be. It only knows the motor configuration, such that it's a hexacopter. And we believe that that was a result of the instability, and then it was unable to control itself and maintain attitude. I would now like to move forward into the budget of the Vesta system. We were allocated $2,000 and projected that we would spend $1,930.25. This is 96% of our total budget. In actuality, we spent $2,060.82, 103% of the total budget. Of note here were the 6 motors and 7 batteries that we purchased. They were the most costly items. They have the benefit, however, of being reusable for future capstone projects. And the reason that we exceeded our budget is because we had to purchase a 7th motor as we burnt one of them out during a 100% throttle test. And we had to purchase many more electrical components that were fried during testing. Now moving forward into lessons learned, we may not have been successful, but we had a very good experience throughout this past year. We've learned that we need to be prepared for things to go wrong during testing so that we can bounce back quickly. For example, we did this with the aerial structure failure and replacing the one center plate with two center plates, but as failures continued to happen, it was harder to bounce back as quickly. We also need to factor more than a 4% margin into the budget so that when we have to buy replacement parts inevitably, we have enough money to do so. We also need to begin software development as soon as possible. If we had spent more time learning how the PIXHawk 2.1 works, we may have had more success during a translation test. We also learned that even if you don't think you have time, you really should make replacement parts. We ended up breaking a total of 4 of our T-beams and having to refabricate them. During that failed test where we crashed, we determined that 3 of the T-beams broke, and all 3 of these were T-beams that had lightning holes in them. The replacement T-beams that we removed those lightning holes on didn't fail. So if we had all 6 without lightning holes, we likely would have survived that crash. We also need to accurately assess the workload. A good example of one of the many cases where this happened is that we only had 1 person assigned to work on the control lock consistently, whereas that's a task that we learned is much more suitable for 3 or even 4 people. And then finally, when working on a multi-team project, it's imperative that there's communication at all levels of the design, not just the mission level. A good example of this is the payload interface and the intense amount of integration that is required to make sure that both systems come together and can safely travel during flow. And at this point, I'd like to share the Invictus labor hours. They totaled 5,007, with the majority being in engineering, 1,899 hours. Engineering hours were any hours spent outside of class working on the design of the system. We would also like to acknowledge our fantastic capstone professors, Dr. Julio Benavides and Dr. Matthew Haslam, as well as everybody listed on this slide for their contribution to the Rogue One mission. I would also like to thank the panelists for their attention during this presentation. And at this time, I would like to welcome up my fantastic colleagues to answer any questions that you may have, as well as Jonathan Hamburger, who presented earlier today.
Just to start off, congratulations. It's a very interesting project. I'm very sympathetic to projects that don't go as planned. You can still learn something from. I'm curious, I believe what I got was that the flight controller you used might be not able to handle the inputs needed, so that might have been causing instability. Do you believe that a different flight controller might have been a better choice?
In actuality, we think the PIXHawk 2.1 was probably the best choice for this design. It's more that we didn't have enough time to understand how all of its systems worked. For example, with relation to that full throttle thrust test, there are commands that you can give the PIXHawk to directly control the throttle, but because of debugging, we were never able to get it to work. If we had more time to work with the PIXHawk 2.1, we think that it would have been more than capable of doing what we needed it to do.
Just a comment to the panelists, we are run on time, so we have 15 minutes for Q&A.
Good sentiment. Congratulations, very well done project. My question is for the structures team. Regarding the requirements in load capability, it looks like those were determined purely based off of the load strength of the material based out of ANSYS, but it doesn't look like you accounted for the factor of safety required for design. Could you comment on that?
Yes, for that I'd be happy to pass it off to either Jason Hamburger or Lucas Siskowski, whichever one would prefer.
So the question, pardon me, was factor of safety considerations and the material choice. So in terms of the landing leg and the landing system, what we did to generate this requirement was we performed a drop test. And so initially, when we were flying to the Aberfour ruins in the fenced enclosure, we knew we had to get over a 8-foot fence, which is about a little under 3 meters. So we did a 3-meter drop test, collected some results, and figured that we needed to withstand 12,740 newtons if we had a free fall. And so when designing the landing legs, we were trying to accommodate if we had a free fall crash from 3 meters, could we withstand it? And so that was a lot of the analysis of, and so that's a lot of what went into it was, okay, what material will help us meet this with our weight requirements? What will, and just the various different factors. And so we did look at a factor of safety in terms of our maximum stress that resulted from these analysis, and looking at the ultimate tensile strength and seeing if we were within a marginal factor of safety for the mission. Does that answer your question more or less?
It does. I'm just curious as to why you're looking at the ultimate stresses versus the yield stresses.
Mainly just because the design of the requirements were for fracture, which we initially should have gone a different route when choosing the requirements.
Thank you.
Thank you.
Okay. Really liked a lot of things about what you did on this project. The use of rice bags to apply load, eloquently simple, good job there. I like your lessons learned. I think you captured the challenges around teaming and integration and team dynamics. You have a large team here, so I suspect that was a challenge along the way. Actually, 2 questions. Along the lines of structures, I saw your ANSYS models of the components and I didn't see any high stress concentrations. How did you fasten the ribs to the base plate? What type of fasteners did you use?
They were fastened with quarter 20 bolts, and there's washers and nuts between each plate to space it and reduce the stress that was applied to each plate.
Okay, and was any analysis done in terms of the entire structure as assembled? And did you find anything in terms of did you do the modeling and what did you find?
For that, I would like to pass it off to either Jason or Lucas Siskowski, whichever one again would prefer.
So in our preliminary design, we were able to do a full system analysis, because we were using ANSYS APDL. When we shifted to a more modular design with combining the center plate and the arms, we didn't have that capability with ANSYS APDL. After our CDR, we were advised to look at ANSYS Workbench, and so due to time constraints, we were only able to analyze the T-beams, which were a wet layup with carbon fiber, and so those were the more critical considerations for us. So we only had time after the CDR really to analyze the T-beams. But in terms of the, so we never really got to a full current this system integration stress analysis.
Okay.
If Lucas has any other comments.
Just to add on to what Jason was saying, shortly after the second semester began, originally the aerial structure was supposed to be just one part, not made of 6 different T-beams. Jason and I were lucky enough to begin fabrication early and just attempt to make a 1/3 scale of that, and found it to be relatively impossible, at least for us. Originally it was, like last semester, we did have it at one piece and analyze it as that, but due to time constraints and changes, we just ran out of time, simply.
Okay, good lesson learned, right?
Yes, absolutely.
All
And
right.
we're very happy that we started fabrication earlier, otherwise I...
Tried proof of concepts.
Yeah.
Excellent. Okay, one more question. In the beginning of the presentation, you made a brief mention talking about conformity inspection of the final system. Can you explain exactly what you mean by conformity inspection and what was done?
Certainly, sir. So what was presented earlier today included what all of our assembly drawings and part drawings were that were handled by the integration team with help of each team. The conformity inspection was to go through all of the parts that we had numbered and designed into the system and confirm that when we fabricated the system, we did it to spec and everything matched what our paper design said it should be.
Okay, and so you didn't find any non-conformities that you had to disposition?
So the conformity inspection was conducted by Dr. Benavides himself, and the results of that inspection were that all of the parts were there and fabricated correctly, but we needed to make updates just to the documentation, things like fixing page numbers or part numbers that were mislabeled.
The reason I bring it up is because it's critically important. You can have the best design and the best hardware, but the documentation and ultimately the acceptance, you're calling it conformity, the acceptance doesn't pass, you don't fly. And you're going to find that that's the case in the highly regulated aerospace industry, space industry. There's a lot of emphasis placed on it, and it's important, and I'm glad you brought it up, so thank you.
Thank you, sir.
Just a quick comment, that photo was taken during my conformity inspection. I spent about almost 8 hours analyzing all their documents.
I'm very impressed. You guys did a fantastic job.
Thank you, ma'am.
Yeah. And that was a lot to go through. I know it takes a lot to trim down information to try to present it to someone that has no idea what your project is. So, one other kudos specifically for the prop and ACS section. I really like the explanation and justification for your attitude requirements or for your requirements in general and the intent behind them. And more importantly, I think you guys had mentioned, the investigation and findings of your flight failure and what you do differently to improve on writing those requirements. Because a lot of the times, when you come into a project, you don't come in at the start of generating those requirements. You come in detailed design and you're building it, and then you have to verify those requirements that other people generated, and you're like, why did they write this way? So that was really good for me to hear. And then great lessons learned, especially with being prepared for failures, and then budget margin and sparing. If you have the money to do it, a lot of the time it's worth getting a spare of a critical component. So for the Vesta System validation section, whenever I hear descent velocity is higher than what the requirement was or as expected on Mars Science Laboratory, when we were landing, we actually found that we landed a lot slower than what our nominal speed was. And at the time, we were like, all right, that's okay. Did some reconstruction, and turns out we overestimated gravity at the Gale crater rim. Imagine what would have happened if we underestimated it, right? So when I saw, I was just wondering why your test descent speed was so much greater than your requirement by over an order of magnitude, and then would you do anything differently, either with the test or the requirement itself?
Yes, so in this case, what was presented as our descent velocity was from that crash test. This taught us a valuable lesson that we set a lower bound for the descent speed, and the reason that was done was to meet what our time constraint was for flight. So we constrained ourselves to a 5-minute flight time to generate requirements and push the design forward. And then we failed to set what a maximum descent velocity would be. So we met the requirement, but not necessarily the spirit of it, because obviously coming down at about 6.3 meters per second was not something the system was able to handle.
Yeah, and I can't remember in your lessons learned if you said anything about requirement generation and revising requirements and thinking more about that, but that is a fantastic lesson learned. So and it applies to real life clearly.
Absolutely. Thank you, ma'am.
Nice job. I have a question about the wire harness. I was wondering if you guys could talk a little bit about the design of the wire harness and then estimated versus actual design and mass, and what did you learn from having to put in all those wires and putting the entire harness together on the system?
Could you repeat that question? I'm not sure I understood what the word was.
So all those wires on there, that's typically referred to as the harness, right? So could you speak to the design and then lessons learned in terms of maybe mass and just general about the harness?
Absolutely. So Kyle Walker and Jonathan Hamburger did a very good job of speaking to professors and putting in a lot of work to have really an electrical engineering quality level of the design for our wiring. And because of that, I would like to pass it off to them, who are really experts in that field. And then Kyle or Jonathan, which one of you would prefer to handle this? All right, thank you.
So for design, we looked at the components that we had, and we designed the onboard computer subsystem to manage all of those, be able to accept all of the components, electrical components that we needed to conduct the mission. We then spent many hours in professors' offices figuring out, I guess, like safety features to include in there, like where to place fuses, things like that. As far as actually making the, cutting all the wires and assembling it all, that was about a 15-hour process for 3 of us consistently working. I believe it was, we weighed it before and then after. It was about 200 grams, I want to say, of wire. Yeah.
That's correct.
So does that answer the question?
Sure.
And do you have anything to add, Kyle? Okay.
Thank you, John.
And then I wanted to get clarification on there's a requirement about the onboard computer having to have at least half a gigabyte of memory, but then you said that you needed to add all this stuff. So let me ask you this way. If you only had a design that had half a gigabyte of memory, would you have been able to perform your mission?
The short answer is no, but I'd like Kyle to go into more detail with that.
No, we would not have. Originally, when we generated that requirement, we only considered the software that we would be writing and the amount of data that we predicted we would collect during a flight log of the Vesta system. We did not take into consideration the various Python libraries that we would need in support of our software, and so that requirement was improperly generated.
Okay. So that's an example, a very valuable example on verification versus validation. While you have verified your requirement, your design, your system was not validated in that sense. So I just want you to really understand, you can have a requirement you verify and then you still don't meet mission success. So in that case, the requirement probably should have been rewritten, and then I don't think you didn't validate it because if you would have had just a half a gigabyte, you would have been able to meet it. So it's a very important thing to understand between verification and validation.
Thank you.
Okay, so you came up with the 12,000-ish newtons based on your going over that fence that was 3 meters. Then why did you, during your test, say go up to 5 meters?
So that was determined mostly because of constraints within the hyperlane. So we determined that we needed to ascend to a minimum of 3 meters altitude, but then while we were operating the vehicle, we saw that there was fluctuation in the altitude. So we didn't want to risk saying go to 3 meters and then we would dip a little bit as we passed over the fence and collide with it. So it was more of a margin of safety. But we wanted to design the landing system for no more than 3 meters drop, because anything more than that would result in an excessive design of the landing system. As we don't expect that failure to occur, but we wanted to have a little bit of redundancy built in, if that answers your question then.
Yes, not necessarily satisfactory. But, I mean, if you're planning on, yes, I understand, you plan to go over the fence, but obviously you gotta, clear it. So your design should have been, okay, you know, my maximum height that I could fall from is 5 to 8 meters, and therefore if you had this, mishap, it would have been survivable. So that was one thing. And whose pocket did the $60.82 come out of?
Well, fortunately, the way that we designed the budget was such that there was a $500 reserve for the whole mission. So while we exceeded the budget for the system, we didn't exceed the budget for the system of systems, the whole mission itself. We were able to pull from that reserve fund to deal with some of that excessive cost that we had.
Okay. And my final question is, your numerical result for the total mass was under the 9.5 kilograms. So you did all that work in your CATIA or ANSYS or whatever you did it in. And then you weighed it at 8.92 kilograms. Why was there a mismatch?
So fortunately, a lot of the things we fabricated were much less weight than we expected them to be analytically. And I believe, Lucas would like to talk about that.
I suppose it's like a fabrication technique, so simply Patrick has some magic carbon fiber and AXFAB. When I was laying it up, I also made sure not to smother the thing in epoxy too, which most certainly dropped some weight. Other than that, luck.
Also, when using the CATIA models, that's using like nominal carbon fiber properties, and so it's possible that Patrick had an off-brand or that's slightly under nominal properties that accounted for some of those weight differences.
So during the preliminary and detailed design, did you have like your maximum expected, the maximum possible, and work it so that it would always come under that 9.5?
Well, we actually experienced a lot of difficulty meeting that 9.5 during the preliminary design phase. There were many times that we ended up exceeding it and having to come back and redesign and try to figure out ways to cut weight. An example of that is the fact that we put lightning holes in the T-beam. It might be difficult to see, but in this one here, this is one of the ones that fractured, and it fractured at the end with one of the holes. And so once we fabricated these and we determined that they were much less weight than we were expecting, the replacement parts, we then removed those holes, and they were still less than we predicted from our preliminary design.
All right, good job.
Thank you, Manny.